The thing I'm presently working on is the periodic table that's on our Quasical website. It's kind of a work in progress. I find I keep kind of adding to it. Right now, I'm working on adding more about, the physical, chemical, biological properties of each element. But the reason for putting it together was to try and visualize the atomic orbitals. And that whole foray began with trying to understand why oxygen as a molecule is so incredibly paramagnetic, why it responds so strongly to magnetic fields that if you pour liquid oxygen through between the poles of an electromagnet, they won't fall under gravity. They'll literally stick to the electrodes because of the magnetism. That was really intriguing to me because, according to molecular orbital theory, there are only two unpaired electrons in the oxygen molecule in the antibonding molecular orbitals. But then, some metals like manganese has five unpaired electrons, 5 or 6, chromium has 6, and it's not nearly as paramagnetic as an oxygen molecule. And to me, that there had to be more to that story. And also, so that's currently what I'm working on, is the magnetism thing. And it's really interesting that if you look, for those viewers who don't know what paramagnetism is, it's just when you have an unpaired electron and you apply a magnetic field, the electron is going to want to line up to the magnetic field. So if you have an atom with unpaired electrons in it, that atom will not only align with the magnetic field, but it'll become attracted into the magnetic field because you have field cancellation happening between the magnetic field, which lowers energy, so it attracts it in. Almost just about all the metals on the periodic table are paramagnetic because just about all of them have unpaired electrons. So what intrigued me the most is when you look at the D block, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, etc. The strength of their paramagnetism doesn't go with the number of unpaired electrons that they have. Scandium has 1 unpaired electron, and it's the second most paramagnetic metal in the D block, the 3D block, which is fascinating to me. Then titanium has 2, vanadium has 3, but they're less paramagnetic, and that intrigued me as to why it is. So I started looking into trying to understand the geometry of those orbitals to try and see where those electrons are with respect to one another, and whether that geometry, whether the interactions based on their geometry could explain their relative strengths. And so that seems to be coming out of what we've been looking at. At least we now have a basis of a way to look at this geometry that seems to be able to account for that trend, which is kind of cool.
So what if I can summarize this correctly, maybe what you're saying is that the shape, the structure of those atoms themselves is what gives them the properties that we observe here, and not necessarily just the simple accounting of whether there's unpaired electrons or not.
Right. So it's not just about the number of unpaired electrons, it's about where they are with respect to one another and how they're interacting with one another within the atom and between the adjacent atoms that accords their paramagnetic strength. And then I wanted to look at ferromagnetism, which is the difference between the two, for those that don't know, is that if you take a metal that's paramagnetic and you put it in a magnetic field, all of the electrons line up and it'll get attracted into the magnetic field. But when you switch the external magnetic field off, then they'll go back to their random arrangements because they can't hold the electrons can't hold one another in line. But iron and cobalt and nickel are ferromagnetic, which means once you put them in a magnetic field and all the electrons line up and then you remove the field, they keep their mutual alignments, they hold each other in alignment, and that's what makes them permanent magnets. So I wanted to know what's the physics behind that? What's the mechanism behind that? Why is it that iron has 4 unpaired electrons and it's ferromagnetic, whereas manganese has 5 and it isn't? It's paramagnetic. What's the difference? It's not just the number of electrons. So what is it about the geometry happening within the iron atom? So I started looking into that a little bit more. And it's also part of the reason that I built this periodic table the way that I've done, to try and show the geometries, because electron geometries have to be symmetrical. So when I looked at iron, it's very interesting. Iron has 6 electrons in its 3D block. So it has a full 3s, full 3p, and then in the D block, it's got 1 pair and 4 singles. So I was trying to kind of figure out what's going to happen in those orbitals in order to make a perfectly symmetrical arrangement, and would that be able to account for its strong ferromagnetism? So we're all familiar with the concept of hybridization from the second shell, how the sp3 hybridization in carbon, makes a tetrahedral arrangement, right? So that's the s and the p orbitals get together to make this. It's not, the s and the p orbitals don't remain separate when they're in the second shell, when they're in the same orbital, because these electrons are in the same shell, so they're going to interact with one another. Looking at the single electron hydrogen atom and then extrapolating up to elements with multiple electrons, and they're not necessarily going to do the exact same thing. So when you look at iron, I tried all sorts of different ways of thinking about hybridization with the s and the p and the d orbital and how that might work. And I came up with a very interesting construct that involves PD hybridization, that the p and the d orbitals are not going to ignore each other when they're in the same shell. They're right there. They're not going to be superimposed with these different geometries. They're going to interact. Mm-hmm. And when electrons interact in the same shell, if they can pair, they will. If they have opposite spin and they can pair, they will pair. Because a dielectron, according to the whole theory that John and Viv and these guys have been working on, dielectrons are incredibly stable. They drain magnetic energy because they're anti-parallel, so they become very stable. So in looking at the third shell of the iron atom, if you look at the p and the d orbital, the p orbital is full, so that's 3 dielectrons, and then the d orbital has 1 dielectron and 4 singles. So if you combine them, that's 4 pairs of electrons and 4 single electrons. That's 8 electron domains. So I was trying to think of how that could be set up in the most symmetrical stationary wave structure, harmonic resonance structure. And this is kind of what I came up with just for those p and d orbitals in the third shell. Now you'll notice there's 4 green and then 4 clear directions here. Both of those are tetrahedral. There's a tetrahedral arrangement of 4 dielectrons and a tetrahedral arrangement of 4 unpaired electrons.
So just for people who are listening, he's holding up what looks like 2 overlapping tetrahedrons, which are symmetrically offset.
This would be a single tetrahedral arrangement in 4 directions. And this would be 2 of those that are superimposed through them, but in 180 degrees apart. So this is really a cubic arrangement. There's the 8 corners of a cube. You could see it, where every corner alternates between being a dielectron and an unpaired electron. So it turns out when you put iron when you make a crystal out of these, well, there's a little bit more to the story that I should say. We have to remember that these are metal atoms in a metal crystal. So there's still a 4th shell. The 4s2 electrons are the ones that delocalize to form the metallic bond. So you have a background matrix of this electron density, the conduction electrons, which is the valence electrons. And now you have these atomic cores without their 2 valence electrons, which have a positive charge. And those are going to be suspended throughout the crystal by mutual repulsion and by attraction to the electrons around them. But what's so interesting is that this arrangement that I showed you with these third shell electrons, these are on the surface of the atomic core, because the 4th shell valence electrons have now delocalized. So in a sense, they've become almost like valence electrons of the core, if you know what I'm saying. So the surface of those atomic cores has unpaired electrons on them. Now, manganese and chromium, the others all have those also, but they're not ferromagnetic. So if you look at the iron entry on our periodic table, which, by the way, the password is Ferromagnetism for that. It's password protected, but for your viewers, they can.
We'll put a link in the description.
We're still working on some of the details and some of the, aligning with observation, so I haven't made it totally public yet. But the concept is that it's not enough that the core of these atomic cores have unpaired electrons, because they're still separated from one another across, that interatomic distance. So that's what paramagnetism is, that if I put that into a magnetic field, they'll all line up. But then when I remove the magnetic field, they can't talk to each other. Their spins can't interact because they're too far apart.
So these ones are actually crystally in contact with one another.
Right. So that means for iron to be ferromagnetic, these unpaired electron orbitals have to be extended outwards, radially outwards into that interatomic space in order that they can link up with one another. So how is that happening? Why does that happen in iron, but it doesn't happen in others? So if you look at the geometry on my iron entry on my periodic table on Quasical, you'll see that, first of all, in this third shell, there's 4 unpaired electrons, but there's also 4 dielectrons. Now, dielectrons have a double negative charge. That's 2 electrons in there. So they're repelling the single electrons much more strongly. So those single electron orbitals are going to be constricted from the sides. They're being squashed inwards. The dielectrons will take up more space. The dielectron tetrahedron will take up the majority of the volume. And then those unpaired electrons are going to be squished. And just like, the figure skater bringing her arms in, where it makes you go faster. If you take a cylinder and you make it squash it in thinner, it'll go longer in response. It'll push the electron density a little bit further outward. But there's more to it than that. That is not enough by itself. If you look at the second shell, just within that third shell, it also has a full second shell. That's a tetrahedral arrangement of 4 dielectrons, and they are aligned. The dielectrons in the second shell are directly underneath the unpaired electrons in the third shell, because that's how they minimize repulsion. But that means that those unpaired electrons have a dielectron repelling them from beneath and dielectrons constricting them and repelling them from all sides. There's only one direction that they can extend, and that is radially outward. So that is what we are proposing, and that is that the reason that iron is ferromagnetic is because it has orbital constriction from the sides and from beneath, which extends those unpaired electrons into the interatomic space, allowing the adjacent iron atoms to parallel spin bond with each other in the same way that we explain for Hund's second rule for the stabilization of parallel spinning electrons in the same orbital. So they create a bond, and then when you align them with an external magnetic field, those alignments they link up, and when you remove the magnetic field, those spins remain. They are interacting with one another, so they hold each other in that spin alignment, and that is why iron, in our proposal, makes a permanent magnet.
I like it.
I like it. I like it too. I like it
cool.
too.
And it's fascinating because if you think about the whole iron crystal as a whole, I mean, this is probably hard to see, but this is like a cubic. You can see each of these green things has 8 points on it. So that would be like our cubic iron atoms. It makes a double tetrahedral arrangement that in one direction through every iron atom, you're going to have a crystal, a tetrahedral crystal, just like diamond, the same structure as a diamond crystal. You're going to have a tetrahedral crystal of unpaired electron, spin bonded, linked, a resonance of unpaired electrons throughout the crystal. And then anti-parallel to it, you have the same diamond-shaped tetrahedral crystal of dielectrons going in the opposite direction through every iron atom. You have a double tetrahedral arrangement of not only unpaired electron spins in a diamond crystal, but then you have non-bonding dielectrons in an antiparallel one, and that's going to serve to constrict those channels where the unpaired electrons are. So you have a very concentrated diamond-like crystal resonance of spin throughout the iron crystal, which is why it gives iron such a disproportionately strong ferromagnetism. It's the most ferromagnetic by far. It's much more ferromagnetic than cobalt and nickel are. And what's also interesting...
Is it more than neodymium?
Yes.
Really?
Yes.
Why are neodymium magnets so thought of as so strong?
Well, neodymium magnets are not pure neodymium. They're neodymium plus iron plus something boron. I think.
Sense.
So pure neodymium has an interesting property called spin glass, where the magnetic domains kind of wander around and they independently and they change over time, which is kind of an anomalous thing that's been discovered. I haven't yet looked into that, but my intention is that to try and see whether this model accounts for what's being observed. One of the things that's observed is very interesting, and that is if you look at the melting point of iron, cobalt, and nickel, and you look at their Curie temperature, which is the temperature at which they lose their ferromagnetism, right? Iron, the melting points, iron is much stronger than cobalt, which is stronger than nickel, higher temperature. But in terms of the Curie temperature, cobalt has a higher one than iron. which means that while iron will take the highest temperature, iron will melt at the highest temperature and then cobalt lower. But cobalt will hold on to its magnetism to a higher temperature than iron will, even though iron has a stronger ferromagnetism than cobalt, which is very interesting. So it seems that this can account for why. I don't necessarily want to go into the details of it, but it's very interesting that iron has this tetrahedral relationship and it makes body-centered cubic crystals. And body-centered cubic crystals, when you turn them at their angle like this, you can see it makes a double tetrahedral structure. So body-centered cubic and tetrahedral are the same crystal structure, but cobalt is hexagonal close packing. And that's because the cobalt electron configuration is more hexagonal. Its three unpaired electrons are trigonal planar. So that means in their crystal, it's going to have corners where you have 3 electrons spin bonding together. Even though there's fewer connections per atom, those connections are 3 electron connections at those corners, which means that those spin bonding is going to be much stronger and it'll hold its magnetism longer. And whereas iron only has these 2 electrons from adjacent atoms, it has 4 of them per atom. So therefore, it makes the crystal interactions are much stronger, which gives it a higher melting point. So as we look at these observations and try and match it up with the ideas, it seems to be holding water at this point. And the other observation that we're looking at is the easy versus the hard directions of magnetization. If you take an iron magnet, if you try and magnetize iron, there's certain directions in the crystal that it'll be easier to magnetize than others. Some will be hard, will require more energy to magnetize. So we're also looking at, does this model account for those differences? And so far it seems to be holding together. So